From the simulation, you can find that their magnitude frequency characteristic of the current can't reflect the fact that the two circuits have the same quality factor. Why? There are two reasons. The first is the resonant frequencies of the two circuits have very large difference. The second is the maximum value of the current of these two circuits have a large difference. In order to reflect their quality factor in magnitude frequency characteristic, we should do normalization, not only to the horizontal axis, but also to the vertical axis of the frequency characteristic. Okay, let's start the normalization. The resistance in different RLC serial resonance are different, so the maximum values in vertical axis are different, which makes different RLC serial resonance circuits can't be compared with each other. The vertical normalization is the magnitude of the current over the magnitude of it in resonance. It makes that the magnitude of current in resonance is always 1 in any resonance circuit. Let's do a detailed derivation. The numerator and the denominator are both divided by R, and it equals this. Do you find its part is omega L over R, this part is 1 over omega RC. It's very similar to the first definition of the quality factor, which are omega 0 L over R and 1 over omega 0 RC respectively. So it can be multiply and divide omega 0 respectively. After this, according to the first definition of the quality factor, we know these two parts are both Q. The magnitude frequency characteristic of the current can be written as this form. Then the horizontal normalization is eta equals omega over omega 0. The resonant frequency of different circuits are different. With the new definition, all the circuits are resonant when eta equals 1. Then the magnitude frequency characteristic of the current is transformed into this form. You see, the resonant frequency of any RLC serial resonant circuit is omega 0. Of course, different circuits have different omega 0. The horizontal normalization enables that all circuits are resonant when eta equals 1. When eta equals 1, the value of this function is 1. In other words, the maximum value of the magnitude frequency characteristic equals 1 for any resonant circuit. It's a result of the vertical normalization. What's the advantage of the normalization? You see, it's the magnitude of the current and also a function of Q. What's the difference of the magnitude of the current with different quality factors? The magnitude of frequency characteristic when Q equals 1 is like this. The circuit is resonant when eta equals 1 and the maximum value is 1. When Q equals 0.5, its magnitude frequency characteristic of the current is like this, a little wider. When Q equals 10, it's like this, very narrow. The horizontal axis and the vertical normalization enables any circuits to be resonant when eta equals 1 and the maximum value is 1. Then we can judge the value of the quality factor from the width of the magnitude frequency characteristic. The larger quality factor is, the narrower the magnitude frequency characteristic is. In future applications, you will find the circuit with narrower quality factor has better selectivity. This is called the general resonant frequency characteristics. It will often appear in signal processing courses in the future.